One of the challenges I had when I was trying to help organize this meeting is that I found I reached out to them, asking them to get involved or share announcements about a comparative climatology of terrestrial planets. Some of them responded like, well, Titan's not a terrestrial planet. Pluto's not even a planet. All sorts of crazy stuff like that. So I've been excited to see that we've got some people here talking about Titan, because we can get in a lot of Titan and Pluto and other planets, because we can get in an argument about semantics if one wants about what the word terrestrial really means. But I really think there's a lot of commonality for any planetary body that has a solid surface and an atmosphere that's roughly on the scale of what we think most of us in this room is terrestrial. I mean, these things all have gray boundaries, and when you get up to super Earths and head off into super Neptunes and stuff like that, there's a lot of great fertile ground to debate all that, but that doesn't mean we should be excluding things. So I was excited that we've already had two talks who've done a nice introduction as well to start arguing about some similarities between what are often in the community called icy worlds, but I still think of as another set of terrestrial worlds, planets, whatever term you want to use that doesn't get something thrown at me. So I wanted to focus a little bit on showing some similarities between Earth and Titan, and thankfully we've already got a nice introduction to you guys for Titan, particularly that the fact that it has a lot of features similar to Earth. It has a hydrological system. It's driven by methane as opposed to water, but it has lakes and seas just like the Earth does. So I wanted to walk through a handful of things that Scott Rafkin and I have been working on to try to understand the kind of circulations you get over these lakes and seas and compare them to Earth. So first I'm going to talk a little bit about some basic Earth stuff. There's a lot more breezes and circulations and stuff we could talk about, but I was just going to talk about some basic things. If you thinking about lakes, seas on the scale of the Great Lakes, because as Morgan just showed us, they're comparable in size to what we see on Titan. And there are a number of different features that you can get, a number of different circulations. I'm primarily going to talk about lake and also land breezes. People often talk about lake effect clouds, and if I have time, I might come back and chat sort of speculatively about that. But what do we know about some circulations on the Earth? Right? Just to make sure everybody's on the same page of what we have with lake breezes. Lake breezes often occur in the morning, right after sunrise. Land warms up quickly. You get an expansion of pressure, which drives the circulation higher up, trying to flatten out any sort of pressure gradient to balance out the conservation of mass. You end up getting a flow of air, both because you're building lower pressure here, and also because you get subsidence coming this way. And you basically build a circulation where you get divergence of winds over the lake. This is sort of a symmetric thing. Something similar is going on the other side of the lake over here on the other shore. Convergence of air over land, and then you get this nice little flow. And this is sort of a classic lake breeze that you get on Earth. And it builds up sort of a whole system where you have regions where you have, is this the right plot? Or did I mess that up? Well, it builds a whole system. I'm confused by this plot, so I'm going to move on. It builds a whole system, but what we can do is look at actual observations and be sure what's going on. And this is an image of Lake Erie where a lake breeze has started to form over the lakes. And so you can imagine the wind is blowing off the lake, so it's an onshore breeze. It's actually pushed these clouds out. So you can see sort of the line where the lake breeze, then the convergence zone is, just from this kind of image, right? So this is an example of one type of sort of breeze that we see on Earth. Then, oh right, this is where I was trying to line it up. So maybe that is the right. Gotta apologize, guys. I didn't get a lot of practice this week trying to run around doing everything else. But then there's also the reverse system, which is a land breeze, where this often happens in the evenings on Earth, where the land cools off a lot quicker than the lake. The lake stays warmer, and you build a flow sort of this way because you're still evaporating some air off the lake. So we have these sort of two types of breezes that we see on Earth, lake breezes and land breezes. And so we're interested in a lot of things about Titan, because Titan, you've seen some of these images before, has a lot of clouds, it has lakes, maybe the clouds are related to the lakes, maybe they're not. These are the kind of things we're interested in. And so this is similar to what Morgan was showing earlier, that the scale of these lakes, particularly the largest ones, Krakamari, Laigia, and Punga, are similar to the Great Lakes in to rough order and to size and volume. So we just wanted to understand, like, do they generate the same type of breezes, and start getting some initial ideas of what kind of conditions create whatever breezes do form over these lakes on Titan. So I'm going to try to do this quick because no one likes getting bogged down in a model description slide. But basically, we did some initial idealized simulations. So a lot of discussion this week has discussed the challenge of using complex models versus simple models when trying to tackle phenomena that's new. But it is possible to use complex models in simplified configurations that actually tends to be very useful. So what we did is we took a mesoscale model from Earth, basically shut off a lot of the physics that weren't applicable. Things like there's a long radiative timescale on Titan, and for the timescale that we're running these models, we left out radiative transfer scheme. I went in and modified some things to make sure that it was, pressure, temperature of Titan and everything else. And then we put in a simplified little lake scheme so that you could account for the fact that as you get evaporation off the top of the lake, you can cool the lake. The lake sort of responds. It's a simple sort of slab model that sort of simulates the mixed layer, the upper mixed layer you get on a lake or a sea or an ocean. And I'm just showing some curves here to show that as a function of different cooling rates off the surface and different depths, you'll get different amounts of, as a function of different fluxes off the surface and different depths, you'll get different amounts of cooling rates. The dashed line here just says that for the rest of this talk, I'm just going to talk about a 1 meter mixed layer because that's the one that responds the fastest, and so it's just, we don't have to sit around waiting as long for things to happen. The other thing I want to point out is there's lakes of a wide range of sizes on Titan. For what I'm going to show you, we've been looking at a whole bunch of ranges of sizes, but what I want to show you today is a 300-kilometer lake. It's a 2D simulation, so we're just taking a slice here, and at 300 kilometers is comparable to like the size of Laigia Mare. It's the second largest lake, or sea, however you want to call it, on Titan. So I'm just going to stop and walk you through this real quick, even though I'm drastically running out of time already. So I'm going to be showing you some plots like this, and I just wanted to show real quick that, well, you know what, in the interest of time, I'm just going to skip this. What I want to do is just go to the animation and then move on from there. Where are you? So this is a simulation where it's an idealized simulation, so it's sort of arbitrary. We started with a subsaturated atmosphere, and we have the lake, which is marked out by the blue lines here. So the lake is in the center here. Start with a subsaturated atmosphere. There's methane and just methane in the lake. Everything else is land. It's got a Huygens profile for vertical temperature and pressure. Let's start this bad boy up, if I can get the mouse back. Hey, come on, work with me. Well, it's one of those days. I had a nice video. I'll show you this instead. The video just shows that there's a lot more structure than what I'm about to talk you through, because there's small scale, boundary layer, turbulence, and mixing, but that we can still back out sort of a mean flow that what's going on. So these plots is, again, the horizontal distance here, minus 150 to 150 is your lake. And then there's just height over here. On this whole screen, I'm just showing horizontal wind. Green is to the right. Purple is to the left. So we're looking at the horizontal wind in this direction. So the way to read this is, hey, something worked. Your flow comes in this way, and your flow up here is coming out this way. And then we can just basically, by eyeball, can see where the convergence is and back out the vertical velocity. There is a vertical velocity. It's about an order of magnitude smaller than the horizontal velocity, so it's just easier to show it this way. And so what we see is in this kind of configuration, the first day we get this interesting lake breeze that builds up immediately from that initial subsaturated point. You got, sorry, I said that backwards. Land breeze that builds up from that initial subsaturated point, and it's extremely vigorous. That's why I wanted to show the video. It's when it just blows up immediately. Because one of the interesting things, if we're talking about comparisons between Titan and Earth, is that the methane in Titan's atmosphere is much more buoyant because of the different mass of the methane molecule. So the molecule case, it's more buoyant, and is also in how close it is to its saturation vapor pressure. So what you have is a much more buoyant system that initially kicks off. So it looks like on Titan you can develop these land breezes, and they can be very buoyant. But if we all these are 6-hour averages, so I could take out some of the finer details of what's going on in the boundary layer. But if we look 1 day later, which is 16 Earth days, 1 Titan day later, we see that a lot of things have flipped, right? And what's happened here, and I'll go ahead and we see it's flipped. And then let me say that what you're getting here is now you have a sea breeze or a lake breeze, like I talked about earlier. And for the rest of the simulation, the lake breeze and the land breeze sort of fight it out amongst each other. The best way to explain what's going on there is we'll look at the bottom right corner here. Part of what happened is that you got that initial plume, you got all this evaporation from the surface that leads to cooling of the lake. Now you start transferring sensible heat from the air into the lake in response to that lake cooling. So then you also end up cooling the near surface air. So you see here that down here that's colder down here right above, and that ends up driving a thermal gradient from the land over the lake, and that's why you suddenly get a sea breeze kicks in and starts this little fight. And what we're looking at here is 3 days later, where the sea breeze is basically, the way I like to think of it, is winning the fight. And what you've developed is a nice mature marine layer where you've got a lot of water vapor down near the surface. You've got this sort of front, so you got vapor coming off. You got this frontal system right here that's associated with these vertical velocities, and you can see they're very constrained to a spot over the land. They show up nicely constrained, and the temperature, yeah, I know, I need to finish. So the punchline, though, is that in some ways, in this idealized scenario, we've basically recreated this sort of picture here, what you saw in Lake Erie. Now, we're not arguing that we're creating rings of clouds around there, because actually in these simulations the relative humidity is too low for cloud formation. But it's just some first thoughts on sort of how you get the same type of circulations between Titan and Earth. What's probably different is what kicks off and initializes these things, because the insolation environment on Titan is very different, a longer radiative time scale. You don't see the diurnal cycle strongly, so it's probably not a sunset, sunrise type thing that triggers these things. And since I'm running late, I'll go ahead and just leave it there. Thank you.
Okay, so thank you, Alejandro. Time for a couple of questions.
When you showed days on those plots, were those Earth days or Titan days?
Titan days, and I apologize. I should have said that.
And what's the length of those?
It's 16 Earth days.
Okay, thank you.
Yeah. Really? Oh, yeah, I didn't know that. Okay, next time. T-sol.
How large-scale circulation influence your topic, your results, if you include large-scale atmospheric circulation?
Yeah, so that's an interesting question. We wanted to build up from this idealized thing, but the thing I'd like to do next is eventually couple a GCM into it. So that would allow us, it's not clear right now. What we have are some physical processes that could happen because of the states of the surface and the atmosphere. Now the question is, how do you create these particular states at a global, how does the climate system create these states, create the right kind of subsaturated atmosphere? So that's where the interesting thing would be is I'm moving to making this a 3D model, and then also being able to drive it with a global GCM. That would actually allow us to address other questions. For example, it's been hypothesized that there are lake effect clouds on Titan, but lake effect systems on Earth, at least, require large pressure systems coming in that bring cold air that come over warmer water, and that's how you trigger that. I don't think anybody's really done the right work yet to figure out if that kind of system even happens on Titan or not. But we are now building up the tools at the mesoscale to try to test that.